Hello, pre-calculus students. We're going to continue in the section 3.3, looking at real zeros. Today we're going to use the rational zero test, which you used yesterday in part of your assignment to figure out what are all the possible rational zeros in a polynomial. Today we're going to use that to figure out what are the real zeros and also factor. So let's go ahead and look at our first example here. We've got g of x equals 3x cubed plus 3x squared minus 11x minus 10. So using our rational root theorem, we can identify our p and our q. Our p is our constant, and I'm just going to list it as if an absolute value is applied because we apply a positive and negative with the p over q relationships. And q is 3. So refresher from yesterday, p being the constant, q being the leading coefficient. And then we find the factors. The factors of p include 1, 2, 5, 10. And the factors of q include 1, 3. So the possible rational roots for g of x include, so this is where we apply that positive negative p over q. They include positive and negative 1 over 1, positive and negative 2 over 2, positive and negative 5 over 1, positive and negative 10 over 1, positive and negative 1/3, positive negative 2/3, positive negative 5/3, positive negative 10/3. All right, so now we want to figure out which one of these is actually, or maybe more than one, is actually a zero of this polynomial. So we want to figure out which one of these will actually give us a remainder of 0. So in order to figure that out, well, we're going to start testing some numbers. So we're just going to pick some. I'm going to start with 1 just because that's the first one I found. So I'm going to go ahead, set up my synthetic division. The nice thing about this is that we can quickly determine if we're going to have a remainder of 0 just by doing that synthetic division that we looked at in our previous sections. So bring down that 3. 1 times 3 is 3, add. 6 times 1 is 6, add. 1 times negative 5 is negative 5, add. Not a remainder of 0. So that means 1 is not a 0. So now we got to try another. All right, so I'm going to try negative 1. So trying negative 1, bring down my 3. 3 times negative 1 is negative 3, that's 0. 0 times anything is 0. Negative 11, well, that'll give me 11, not 0 here. Negative 1, not a root, not a 0. Let's try another one. So now looking at 2's, I'm going to see if 2 is a root. So 2, bring down my 3. 3 times 2 is 6. Add, we get 9. Multiply, we get 18. Add, we get 7. We can see here we're going to get a remainder. So 2 is not a root. I'm going to try negative 2. So notice I'm just going through and checking which one of these are divisible. So looking at negative 2, bring down that 3. 3 times negative 2 is negative 6. Add. Multiply. Negative 3 times negative 2 is 6. Add. Multiply. Negative 2 times negative 5 is 10. Add. Now we have a remainder of 0. So what does that tell us? It tells us negative 2 is a 0 or a root of this. So in factored form, what I have at this point is x plus 2. And then remember, remainder, constant or number by itself, x to the first, x squared. So this would be 3x squared minus 3x minus 5. The first thing I would check is this factorable? If it's factorable, I'm going to go ahead and factor it because that's quicker than using the quadratic formula typically. For the sake of time, I am going to tell you this is not factorable. So in order to find the other zeros, if this is not factorable, I know that my other zeros must not be rational. They're going to have a square root of some sort. So I'm going to use the quadratic formula. So x equals opposite b, plus and minus the square root of b squared minus 4ac all over 2a. And this simplifies to 3 plus and minus the square root of 69 over 6. Okay, so if I wanted to write this in factored form, our two additional solutions, which are irrational because we have the square root of a non-perfect square, but they still are solutions or zeros to this to this polynomial. This in factored form is x plus 2 x minus our other roots. So one of our other roots is 3 plus the square root of 69 over 6. And our other root is minus. All right, so if we were asked to write it in factored form, this is what we could write. Now we're also going to be asked to find zeros. Well, to find zeros, we can find zeros. We've already actually found them. One of our zeros or roots is -2. Or set this guy equal to 0, solve it, x plus 2 equals 0, x must equal 2, -2 rather. And then our other two solutions we already found here. So I'm going to list those two, and we should see that in factored form, we've got x minus each one of these roots. Minus a negative will give us a plus there, notice. So if we are asked for our zeros or roots, remember those two names are used interchangeable, we would have these for our zeros or roots. One is rational, two of them are irrational. And how did I find them? Well, I went ahead, found my rational zeros possible, and started testing them with synthetic division. Let's look at another. All right, here's our next one. We've got g of x, and it is 2x to the fourth plus x cubed minus 7x squared minus 3x plus 3. And again, I'm going to do my p over q. This one we have fewer to choose from. So p is 3, and the factors of 3 include 1 and 3. And q is 2. Factors of 2, 1 and 2. So when we're looking at our list, p over q, we could have positive and negative 1 over 1, positive negative 3 over 1, positive negative 1 over 3 or 1 over 2, and positive negative 3 over 2. Okay, so these here, we've got 8 possible rational roots, so that's going to be less time, hopefully, even if I had to check more than just a few, it wouldn't take me that long to check which ones are actually zeros for this. All right, so let's go ahead and, you know what, I'm going to start with my 1/2. So I'm going to start with 1/2 here. I'm going to start with positive 1/2. And just because I started with integers on my last one, I'm going to start with my halves here. So I'm going to bring down my 2. 2 times 1/2 is 1, add. 2 times 1/2 is 1, add. Negative 6 times 1/2 is negative 3, add. And 1/2 here is 0. Okay, so this is a 0 right here. And I knew it was 1/2, so that's kind of why I started with that for the sake of time, and so that this video doesn't have me going through 5 different zeros before I get to this one. I went ahead and just showed you the one that is a 0 right away. We could have also tested out 1, -1, 3, -3. Those are not, for this one, those are not zeros that I'm going to start with. Now, one of them is a 0, but for the sake of using a fraction, I went ahead and started with a fraction. All right, so what do we have here? Well, right now I have x minus 1/2 because that gave us a remainder of 0. And then again, we have remainder, number, x to the first, x squared, and x cubed. So then this is 2x cubed plus 2x squared minus 6x minus 6. Now at this point we have some options. Sometimes we will not have options like we have with this one, but in this one we do have options. I notice here that these two both have the same coefficients, and so do these two. I also notice that this sure looks like it might be able to be factored by grouping. So I'm going to go ahead and factor this by grouping. Now, if I didn't notice that I could factor it by grouping, what we could do is we could continue to synthetically divide with these coefficients and then see what other zeros remain. And I'm going to show you an example of this after I go ahead and I factor this by grouping. So I'm going to go ahead again and factor this by grouping. These have a GCF of 2x squared, so we can factor out a 2x squared here, and when we do, we get x plus 1. These have a GCF of -6, and I know I want to take out a -6 or factor out a -6 because in my parenthesis, remember, I want the same. And if I have a -6 divided by a -6, I'm going to get that plus 1. All right, so then this factored even further is x minus 1/2, x plus 1, 2x squared minus 6. All right, let me show you another option. Again, if we could not factor this, or if this was not factorable, then we could go ahead and continue solving what we have here, or trying to synthetically divide what we have here. And we would see, I'm going to go ahead and I am going to use -1 as a 0 or a root, because I already know based on that, -1 should give me a remainder of 0. So if we couldn't factor, we could continue to test some p's over q's and see which one or ones are in fact zeros. So let's go ahead and do that. So bring down that 2. 2 times -1 is -2. That gives us a 0. Anything times 0 is 0. Add, we get -6. -6 times -1 is 6. Notice we have a 0 for a remainder. And if we continue to synthetically divide, we could divide out more roots. So this is another option. This would give us 2x squared minus 6. Notice that's what we have here. So this is our factored form. Now I also know you could factor out a 2. So if you wanted to factor out a 2, you certainly could here. And you would have 2 and then x squared minus 3. All right, I would accept either of those. I kind of like the 2 factored out, so let me actually just write that 2 factored out, because that technically, one could argue, is completely factored because the GCF is removed. All right, so let's talk zeros. Zeros in this. All right, pen was freaking out there. Now let's go back to zeros or roots. Remember, those two used interchangeably with this. So here, these two are fairly easy to notice, right, and to identify. We've got a 0 or a root of 1/2. We also have a root of -1. And here, x squared minus 3, if we were to solve this, we would have both positive and negative square root of 3. So these are the 4 zeros, 2 that are rational, 2 that are irrational. All right, one thing that I do want to point out, example 3.3.3 in your book does go through using a graphing calculator to find zeros or a 0.